Okay, good morning. So let's start with some questions. So which of these describes a colloidal dispersion? Okay? Yes? All right. And the answer is? Which one? The answer is A. So you can only separate colloids by very sophisticated filtration methods. The particles are definitely larger than simple solutes. So this A also applies to what? Technically emulsions, because they are colloidal dispersions, and suspensions. There's either the particles are enormous, right? B applies to only suspensions, right? C, solutions, right? And D, suspensions or heterogeneous. So a homogeneous dispersion that contains substances of opposite polarity is called which of these? And notice the term homogeneous. Let me look at this. Technically, there could be two answers for this one, but anyway. Okay? All right. So, solution is homogeneous, but the opposite polarity is what throws that one off. Same thing with suspension. Technically, both of these are okay. Emulsions or colloidal dispersions would have a homogeneous appearance, microemulsions as well. So technically either B or C could be acceptable. All right. Which is an emulsion of nutritional significance? answer is all of them, right? Technically, right? I mean, butter, all of these are foodstuffs, and all of them are emulsions, right? Butter is a water and oil, or butter and fat. It's not oil, it's a fat. Similar to mayonnaise, and then milk is a fat and water emulsion. All right, everybody's here? Hold on, why is this not turning on automatically? Hello? I don't know why this is not opening. Strange. I'm confused. This should open automatically. Let's do this. All right, well, I mean, your attendance will be taken because you answered those questions today, I guess. I have no idea what's happening here. All right. So, let's continue with electrolytes and terms related to solubility and things of the sort. So let's focus on solutions for a little while now, because even though bodily fluids, as we've described, contain colloidal particles, and if you look at the blood, there's lots of cells that make it a suspension, the sort of the background of it all is a solution. So we need to speak of solutions when you're working in a laboratory setting, in particular, or analyzing samples of things. The most common type of sample that you will ever be working with is a solution. So when you're talking about solutes, which are the substances dissolved, and we're going to focus our attention obviously on aqueous solutions, you can broadly categorize them into electrolytes and non-electrolytes. So an electrolyte is any substance that upon dissolving in water will produce ions, and those ions will then, by virtue of them being dispersed throughout the solution, they are capable of conducting electricity. So it can be an ionic compound that pre-exists as ionic. It can be a molecular, non-ionic compound that starts molecular. When it dissolves in water, it will break apart into pieces, a process called ionization. Ionic compounds, when they dissolve, if they have a high solubility, the ions pre-exist as ions. Therefore, they simply dissociate, meaning they separate from each other. That's what then generates the ions that are capable of conducting electricity. In the case of molecular compounds, we're speaking of substances that will either fully or near fully ionize, meaning they pre-exist as molecular compounds, and upon dissolving, they ultimately ionize. They produce ions from where there were none before. That process is called ionization. So, for example, hydrogen chloride, when it dissolves in water, it breaks apart, i.e. ionizes into hydrogen ions and chloride ions. This is what then we call hydrochloric acid. And this is now a solution that contains ions. Per mole of compound, you pretty much get 1 mole of H+, 1 mole of Cl-. So this is an ionic solution coming from a non-ionic substrate. Because you have ions in the solution in either case, this is capable of conducting electricity. So when you have these compounds that are highly soluble and dissociate, or near fully ionized or fully ionized, meaning per mole of compound that dissolves, you get an equimolar amount of the ions that are dissolving, these are known as strong electrolytes. Now there's also what we call weak electrolytes. These are molecular compounds, that when they dissolve, they only partially, a fraction of the particles that are dissolved are the ones that actually ionize. The majority of the compound remains intact in solution as the molecular compound that it was, only a small fraction of those molecules that are dissolved will ionize. Therefore, the percentage or amount of ions that are actually released into the solution is very small relative to the amount of substance that's actually dissolved, and therefore the capacity of those solutions to conduct electricity is much weaker than the strong electrolyte. And then the alternative, the other extreme, would be non-electrolyte, meaning these are always molecular substances that they simply dissolve and exhibit zero ionization. No ions are produced from these substances. So the most common examples are organic molecules that do not have any acid-base properties. We're going to talk about acids and bases later. Those will typically simply dissolve and not yield any type of ionic particles in the solution. So you can actually put together a little experiment. We don't do that here, but if you're in the physics department or some other place where they work with electricity, you can actually confirm this. So let's say you have a solution of glucose, for example. Glucose is a non-electrolyte. Okay? It's an organic molecule, doesn't have any acid-base properties. It's not going to produce any ions. So if you put a solution of glucose, and you notice here you have one piece of metal here in the solution, you have a second one. They are not connected. So when you turn on the circuit, the current will be coming this way. It ends here. It has nowhere to go. And therefore, it doesn't close the circuit. The light bulb does not light up. Let's go to the far right. You have a, let's say, NaCl solution over here, right? So the electrical current comes in, enters the solution, and then because there are ions in the solution, up here they're trying to show you how it happens, the ions actually can move between the two pieces of metal that we call electrodes. They're able to actually transfer electrons between the two through the solution, and that's what then allows the electrons to technically flow through the solution. Well, it's by way of the ions. And then it gets to the other side and it goes through the bulb and the bulb lights up. If you compare with a weak electrolyte, here they're trying to illustrate the particle black and red. Most of it remains as such, only a little bit has produced the ions. So the ability to conduct the electricity is much more limited. Therefore, the light bulb doesn't light up as much. Okay, that's a weak electrolyte. So it turns out, if you look in our bodily fluids, we are loaded with a mixture of strong electrolytes, things like sodium and chlorine and bicarbonate and all kinds of different ions, potassium, magnesium. The list is long. Most of the organic materials that are floating in our bodily fluids, whether they're organic molecules or even colloidal particles, they actually technically have charges associated with them. So they're going to be weak electrolytes. And then, as I mentioned, glucose as an example, there's many others. Any organic material that's floating in your bodily fluids that does not have acid-base properties, that will make sense a little bit later, then those substances end up being non-electrolytes. So we need to speak of the concept of solubility, which is simply a description of how much of a substance will dissolve in a particular sample of a solvent. And it's temperature dependent. So if you have a certain amount of solvent and you add solute, the solubility simply is a number that tells you how much of that solute will dissolve in that solvent at that given temperature. Now, we already know from our daily lives how temperature affects solubility. If you add sugar to your hot coffee, it dissolves very quickly and you put more sugar in it. If you add sugar to your iced tea or your iced coffee, good luck, right? You're going to have to be there for a while and go to the bottom. It doesn't dissolve very well because the solubility is temperature dependent. So again, that number, you can put a number to it, is the maximum amount of solute that can be dissolved in a particular amount of solvent at a given temperature. For most solid or liquid solutes, as I have just described, the solubility will increase as the temperature increases. The solubility typically decreases as the temperature decreases. Turns out for gases is exactly the opposite. So if you have a gaseous solute, increasing the temperature decreases the solubility. And this is the problem with global warming, that, as I mentioned previously, the amount of oxygen that's dissolved in bodies of water, as the bodies of water get warmer, the oxygen level goes down because there's less solubility, and that can have a huge impact on marine life. So the rate, this is also completely logical and commonsensical, right? The rate at which a solute and solvent mix will depend on how subdivided the solute is. The more powdered it is, the more surface area is exposed, the faster it's going to dissolve, right? If you throw cubes of sugar into your coffee versus highly powdered sugar, the powdered sugar will dissolve faster, right? Because there's more surface area exposed. And also the degree of agitation, right? If I just throw the sugar in there and just hope for the best and just observe it, it's like watching paint dry for it to dissolve. But if you stir it, like that, right? Especially if it's hot, right? Back to the temperature issue. And again, the rate also depends with temperature. If it's hot, if the solvent is warmer, the dissolving process is faster. Of course, remember, gases is the opposite, right? They will actually leave the solution with increasing temperature. So this little graph is simply illustrating some of these principles. So the solids are in the solid line, and the gases are in dotted lines. So notice for solids, this is temperature versus solubility here in grams per 100 grams of water. So notice for most solid solutes, temperature increases in temperature, increases solubility. And it varies greatly among different substances. So notice, for example, for potassium nitrate, I mean, if you go from room temperature to 40, I mean, it is enormously changing the solubility. Interestingly, if you look at NaCl, sodium chloride, the solubility is increasing, but it's not a dramatic increase in solubility as the temperature increases. There's some anomalies that are difficult to explain why that is the case. Here's an interesting anomaly. Sodium sulfate, the solubility actually goes down as temperature increases. It's kind of a weirdness that we don't know why. It is what it is. And then, of course, with gases, it's consistent. Increase in temperature will consistently decrease the solubility, right? So ammonia, HCl, SO2, etc. Here is some common gases that are out there in nature, among other places. So, for example, again, here's oxygen. Solubility, this is now, because gases, in fact, all of these gases except for CO are completely nonpolar. The solubilities are very, very low. This is millimolar concentration. But the trend is clear, right? As the temperature increases, the solubility increases, right? So, I mean, if you look at 25 Celsius, which is our room temperature, this is about 1.2 millimolar is the concentration of oxygen. If the temperature goes up, 30 is, and in the summer it can go into the mid 30s. It's going down, right? But if our planet consistently keeps getting warmer, then the concentration of oxygen just keeps going down in our bodies of water. So there's what is known as Henry's Law. I believe we talked about Henry's Law at some point in the first semester when we introduced the concept of solutions. Henry's Law is pertaining to gases and simply says that if you measure the concentration of a gas dissolved in a solution, that concentration is directly proportional to the pressure of the gas above the surface of that solution. The higher the pressure, the more gas is technically being pushed into that solution and therefore will dissolve. So it turns out that you can speak of it in terms of concentration. You can also, it's exactly the same as the solubility, because the concentration that you measure at a given pressure is how much of that gas will dissolve at that pressure. So it's technically the solubility, right? So those two terms are synonymous when in the context of gases. The primary example of Henry's law is, of course, carbonated beverages, right? When you buy your can of soda or bottle of, carbonated water or whatever soda drink that you may imbibe, it is under extremely high pressure. They push the CO2 into the solution, very high pressure, and then they seal it while it's still at very high pressure. So a lot of that CO2 has dissolved because it's at pressures that greatly exceed the atmospheric pressure. The moment you open the bottle, the pressure inside the container drops to atmospheric, and then therefore suddenly the solubility of that gas has gone down because the pressure has gone down, right? So if less of it will dissolve because the pressure has gone down, so the only thing that can happen is that the gas starts to leave the solution, right? And that's what then ultimately leads to the effervescence, which is how we describe this process of that gas leaving the solution. Okay? So again, when that container is opened, the lowering of the pressure is what causes the bubbles to form. So this ties to a phenomenon known as decompression sickness for those who go deep sea diving or under any kind of environment where they have to breathe air from tanks at high pressure. What that is doing is that it's pushing air into your lungs, and that then gets transmitted into the blood at high pressures, much higher than atmospheric. And then what that causes is that more air is dissolved in your blood. Okay? So not only does oxygen enter into your blood naturally, so does nitrogen, because nitrogen makes up almost 80% of air, right? Now, of course, the proportion of nitrogen versus oxygen in blood, there's more, the ratio of oxygen to nitrogen within blood is larger than in air because hemoglobin traps oxygen and increases the amount of oxygen. We'll talk about that. But anyway, you have significant amounts of nitrogen in your blood at all times. It doesn't do anything because it's not involved in anything. If you're taking in air at high pressures, then more nitrogen, together with oxygen and everything else, is getting introduced into the blood. So as the diver comes up, it is part of the training and process that you cannot rise to the surface too quickly, because that is the equivalent of opening the bottle, right? And then what happens is that if you have a lot of gas dissolved in your blood at high pressure and you suddenly open the bottle, coming up to the environment, which is atmospheric, to the surface, which is atmospheric pressure, then this is what's happening inside your body, your circulation, your blood. Bubbles begin to form, and those bubbles, as they travel through the circulation, they're going to get trapped in capillaries and all sorts of places, and that can cause stopping of the blood flow, ischemia, right, to the point where it stops at these particular places, and it can cause tissue damage, it can cause loss of limbs, it can cause strokes, it can cause heart attacks, all kinds of things, right? So it's an interesting phenomenon, unclear why exactly this happens, and it tends to happen in that particular part of the body, probably because there's lots of perfusion in that area, but typically in the abdomen associated with the intestines and things of the sort, these divers that this happens to, it's called decompression sickness, they have excruciating pain in their abdominal region, and they're kind of bent over in pain, and that's why it's called the bends, because they just can't help themselves from bending over to try to relieve the pain. So this is entirely the result of Henry's law, and many of these patients need to be brought into what's called hyperbaric oxygen therapy and things of the sort. So in terms of the proportionality constant, let me go back. There's a proportionality constant here that relates that concentration or solubility to pressure. But what is the significance of that constant? Well, what that constant tells you is, in fact, how much gas will actually dissolve at a given pressure. So each gas has its own Henry's constant. It depends on the gas. And it's again, the magnitude is reflective of the ease with which that gas will dissolve. So here you can have two different gases. They're exactly at the same pressure, right? Well, this is what this is trying to represent. I mean, I haven't counted and I'm not going to. But if you were to technically count all the dots in here and all the dots in there, they're the same. So that's what means that it's the same pressure, right? But then notice the one on the left, there's less gas particles in the solution. Here there's more. So this is reflective of the magnitude of the constant. The gas that has a higher Henry's constant, more of that gas will dissolve than the one that has a lower Henry's constant. Less of that gas will dissolve. So typically what ends up happening is that gases that are very polar, because they have a lot of affinity for water, they're going to dissolve to a greater extent. They have higher Henry's constants. Things that are nonpolar, like oxygen and nitrogen and helium, none of that is polar. Those don't have any type of attraction for water. Water is very polar. We're going to start talking about like dissolves like very soon, but you should have an idea that things that are compatible will mix, things that are not compatible will not mix, right? So this is oxygen has a low solubility because it's, it turns out if you then measure its Henry's constant, it's very, very small. So back to these concepts of gases dissolving. Turns out that some gases, and oxygen is not among these. Well, in the context shown here, it is in a different context. Some gases will display a higher solubility than what you would predict based on their structure, their polarity, and so on. Because it turns out that the gases actually chemically react with the water. And therefore, the amount of gas that enters the water, a portion of that will then get taken away by the chemical reaction with the water. So then, therefore, more of the gas, of the intact gas, can enter into the solution. So classic examples are sulfur dioxide and carbon dioxide. Sulfur dioxide has important implications for the environment. It's a public health issue. This gas can go into the atmosphere and react with water in the clouds and in the air in general. That produces sulfurous acid, which is the name of this compound. But then, as we're going to learn in the next chapter, this can break apart into ions. And H plus is what defines an acid in solution. And this is one of the major culprits of what we call acid rain. So whenever SO2 from industrial processes or disposals or improper disposals ends up in the environment, that substance is a gas, ends up in the atmosphere, and then it finds water, and then it produces H2SO3, and then that falls back to the ground. And that then is one of the components of what we call acid rain. So again, the concept of environmental pollutants is a very important concept. When you're working in an industrial setting or even a laboratory setting, you need to be very mindful of the disposal processes of substances, because these things can harm the environment and ultimately the planet. So in the case of CO2, the issue is not acid rain or anything of the sort. In the case of physiology, for example, we're going to learn that this reaction that's shown here, as simple as it looks, it's one of the most important chemical transformations in the human body, because this is one of the reactions associated with acid-base homeostasis in the body, as we're going to learn in the next chapter. So CO2, completely nonpolar. SO2 is polar. So based on polarity, you would expect it to have reasonably good solubility. It's actually higher than what would expect just on polarity alone because of this reaction. But CO2, you would expect it to be like oxygen, like nitrogen, like helium in that graph that we saw, to have very low solubility. Turns out it has reasonably higher solubility than what you would expect for a nonpolar substance because of this transformation, in which it initially reacts with water to produce the compound in the middle is called carbonic acid. Turns out that carbonic acid, they finally fixed the pen. Yay! Carbonic acid. It turns out that the carbonic acid is not very stable and then goes ahead to further decompose into, again, protons and bicarbonate. So if you observe, the skeleton of what was CO2 ultimately ends up contained within bicarbonate, and it's an ionic structure. So this is exceedingly soluble in water. This is the way that water actually is transporting CO2. It's in the form of bicarbonate. About 75% of CO2 is actually in your bodily fluids in the form of bicarbonate. We're going to talk later about the other possibilities. CO2 itself is about 5%, and then CO2 actually latches on to proteins, albumin and others, including hemoglobin. And that also forms a part of the available CO2 in bodily fluids. So ammonia is another example of a compound, very polar, very soluble in water, but not only that, the solubility of ammonia is enhanced by the fact that ammonia will react with water to produce ammonium and hydroxide ions. A proton from the water, it's always good to draw water when you're considering water in particular types of chemical transformations. To write it as HOH, remember ammonia has a little lone pair over here. If this picks up a proton from that, then you get another proton now bonded to the ammonium, and then the hydroxide is left behind. This is a reversible process. But the fact that the ammonia is engaging in this transformation is then increasing its ability to dissolve in the water. Okay? So back to oxygen. I mentioned oxygen is not very soluble in water. Yes, that's true. Very low solubility in water. But in blood, it is about 66 times more soluble because there's something in the blood that's actually interacting with the oxygen, and that is hemoglobin. Okay? So the hemoglobin inside your red blood cells, as we're going to learn in more detail a little bit later when we start looking at protein structure, it has 4 sites. There's 4 sites where oxygen can covalently bind in a completely reversible process, because this is the whole point. To bind to oxygen in the lungs, carry it to the tissues, and then let it go, right? So in the lungs, it's going to the right. In the tissues, this reaction is going to the left, because you're going to release the oxygen. But the fact that there's this entity in your blood that's capable of trapping the oxygen then allows for a very enhanced ability of that to dissolve the oxygen. All right, so let's now delve into a little bit more detail of this concept, like dissolves like. We're going to talk about what's called the hydrophobic effect. We're going to bring in a little bit of thermodynamics to the discussion to explain the hows and the whys. And then we're going to introduce some terminology that we need to talk about, bringing back some of these concepts of amphiphilic, emulsification, and then tying it together with soaps and detergents, and then putting it into a physiological context as well. So this concept of like dissolves like is simply stating that compounds that have similar polarity will mix with each other. Okay? The converse would be substances that have very different polarities will not mix with each other, because substances will try to mingle with other substances to which they have an affinity. Yes? If you have no affinity, meaning you have completely different interparticle forces, then there's no attraction, there's no interaction. Right? It's not going to happen. Right? It's like if you're going down the mall and you see somebody you like, you're going to go in that direction. If you see your mortal enemy, you're going to go in the other direction, because you don't want any type of interaction with that person that you have no affinity, no attraction to. Right? So this is the similar concept. So hydrocarbons will very quickly and very easily mix with each other, but they will not mix with water. They will not mix with other polar or organic compounds for the most part, with some exceptions. So if you have a little container that has pentane, right? Everybody should know what pentane is. Yes, it's a little 5-carbon hydrocarbon, right? 2, 3, 4, 5. And then hexane is 2, 3, 4, 5, 6. The difference is 1 carbon, right? They're both hydrocarbons. They can readily interact with each other. And if you recall the types of attractive forces that exist between pentane and between hexane molecules on their own is what type of interparticle forces? What are the types of interparticle interactions? So actually, van der Waals is the umbrella term. Although some people use that term for specific ones, but it's actually not proper. All of them are van der Waals forces. London dispersion, and that's the one that operates in which types of compounds? Non-polar, right? So the types of forces that are operating here are London force dispersion forces. Oops, forgot the word dispersion. London dispersion forces, right? So, I mean, if you look at the little skeletal structures that we draw, you can actually see it. If I draw hexane and then I draw pentane sort of over it, you can sort of see they can stack upon each other, right? Even though this one has a little extra carbon here, it doesn't matter. They can stack upon each other and they interact. Their surfaces are compatible. They can stack upon each other. And the entirety of what's happening on those surfaces is London dispersion forces. So here they're showing 2 pentanes. Here they're showing 2 hexanes. Again, the little forces are here, right? And here and here and here. Well, they're identical forces, so they can perfectly mingle, right? So hexane and pentane, perfectly compatible. Similar interparticle forces, they're going to be perfectly miscible. They mix with each other. Miscible is the term, right? Again, if you consider polar substances, so organic substances that are polar will, for the most part, dissolve in water, particularly if they're capable of engaging in hydrogen bonding, which is the main interparticle force that exists in water. So substances like ethanol, if you remember the structure of ethanol or methanol, methanol is just a CH3 with an OH group, and then ethanol is a CH3CH2 with an OH group. The presence of this OH group allows for the substances to mix with water because water will engage in hydrogen bonding with itself. The alcohol will also engage in hydrogen bonding with itself. Now, of course, the pieces that are nonpolar, which are these, draw them with a square, those pieces will interact with each other via London dispersion forces, but the OH groups of the alcohols can interact with each other via hydrogen bonds. Because hydrogen bonds are so strong, even that this is ethanol, even that this is carrying a little piece that is nonpolar, the strong attraction of the OH group of the alcohol with the OH groups of the water overwhelms this nonpolar piece and then allows that interaction to happen. Methanol, ethanol, and alcohols with small numbers of carbons. We're going to see that this changes dramatically as the number of carbons increases. They are going to be pretty much fully miscible with water. So alcohols and other substances capable of forming hydrogen bonds will be typically miscible with water because of these situations. So again, it's all about compatible intermolecular or interparticle forces. They have to be similar. When you compare the pure substances, whatever forces they have, if that's the same as the other compound, then you would expect them to mix. So polar solvents will dissolve polar or charged particles. Nonpolar will dissolve nonpolar. But it's these two, nonpolar with polar and vice versa. Those will not mix. Okay? So again, the term is miscible. If substances mix with each other, they're said to be miscible. If they don't, they're said to be immiscible. Yes?
So you said like surfactants can like make things that aren't supposed to mix. Does that
Yes.
apply to this?
we will see that surfactants is actually a third substance that, when added, allows the polar with the nonpolar to mix. We're going to see that in more detail now at the molecular level very soon. All right, so this is where the thermodynamics comes in. Remember what we said, that for any process to be spontaneous, the delta G for that process needs to be negative. Okay? So, for a solution to form, we're going to focus on liquid solutions because that's what's more relevant. Turns out that for gases, these concepts do not apply. The like dissolves like. Doesn't matter what the polarity of the gases are, they're always going to mix because gases cannot be stopped from occupying the entirety of the container that they're contained in. So you can mix methane with ammonia, one completely nonpolar, the other one completely polar in a container. It's going to be perfectly homogeneous, and they're going to be all occupying the totality of the available volume. So these concepts apply to liquid solutions, which is what's more relevant to us in terms of studying processes that happen within the human body. So, a couple things. Solute and solvent must have similar size particles, which is typically the case for a traditional solution. Once the particles start getting very disparate in terms of their sizes, then we start talking about colloidal dispersions, and that sort of is beyond, things get a little bit more complicated as things get different in their sizes. So we're going to focus the discussion on solutions because that's where the solutes and solvent particles are similar. So here's the key that you need to understand. Let me go back to these slides. So I'm going to use this one as the example. So as I said, if you look at a sample of pure pentane and pure hexane, what's happening within the pure pentane? Well, the pentane particles are interacting with other pentane particles. There's nothing else in it, right? And they're interacting with each other, stacking upon each other as they sort of collide and attract each other. Similar thing happens with the hexane. So what do you think technically needs to happen for this outcome on the far right? What needs to happen for them to mix and then suddenly pentane be mixed with hexane and interacting with the other one? What needs to happen? Two things are the same, different compartments. Suddenly they're together and they're interacting with each other. What technically must have happened? So I'll tell you. These technically must have gotten separated from each other, and so did these, and then they combined with the other ones, right? So in theory, what needs to happen for a solution to form is that, let's assume there's more of this one, right? So let's say this is the solvent and this is the solute, just for argument's sake. So the solute particles need to separate from each other. The solvent particles need to separate from each other. And then the solute and solvent must come together and attract each other. This is what technically needs to happen. Now, separation of these two, anytime you separate something, typically you're breaking bonds, non-covalent, but they're bonds, interactions. Anytime you disrupt interactions, that requires an absorption of energy, because that requires work to get them off of each other, right? Same thing here. Work, energy is needed to separate them. So this process requires an absorption of energy. This process requires an absorption of energy to separate them. When they come together, energy will be released in the process. Now, whether more or less energy is released when these two come together relative to what was required to separate these two in their own realm, that depends on the relative magnitude of the attractions of these two relative to the attractions of these two plus the attractions of these two. So the net change in energy, whether the whole process absorbs or ultimately releases energy, meaning endo or exothermic, depends on the relative strength of those attractions. Okay? So you must disrupt two attractive forces for which energy absorption is required. You need to separate solvent from solvent, You need to separate solute from solute. And then these two forces have to be replaced by forces that are of similar magnitude as they come together. And every time two things come together, that delta H is negative. So the totality of the positive delta H associated with the separation of these two, when you combine that with the totality of the energy released when they come together, that's going to give you the net change. It can be positive or it can be negative, depending on the strength of that attraction. That's what this is saying. Okay? Now, we haven't talked about entropy. That interaction must ultimately yield also a net entropy change that, when combined with the enthalpy change, as long as this delta G is negative, the solution will form. Okay? So let's look at the enthalpy consideration first. This is very cartoonish and hypothetical, but let's assume we have a solvent and a solute that need to form a solution, right? So again, in theory, what needs to happen? The solvent particles need to separate from each other. That requires energy. So we're here, we're going to have some type of energy absorption. Here's our solute. These particles need to separate. Here they're illustrating it as a solid solute. Particles are very tightly tied to each other. To separate those particles, some type of energy needs to be absorbed. So there's a delta H from solvent separation, there's a delta H from solute separation. Both are positive. Now you have the two particles that have theoretically been separated. When they come together, if the energy released when they come together surpasses the energy that was absorbed to separate them, then technically you have a net loss of energy towards the surroundings. That produces an exothermic solution formation process. And how do you detect that? In the laboratory, you did this already. It gets warm, right? So when you mix the salt or whatever it was, and you stir and you touch the container, or if you had a thermometer in there, either way, you don't have to touch it if you want to. Just do it by thermometer, right? If the temperature goes up, or if you feel it getting warm, that means that the energy that was needed to separate the solute and solvent, when they come together and mix, if an excess of energy is released, then heat is released, right? That excess is heat. It gets hot. That's exothermic. You could have the opposite, and you did this in the lab. You mix two substances, a solute and a solvent. The energy that was needed to separate the solvent combined with the energy needed to separate the solute, when they come together to form the solution, there's a deficit. So more was required to separate them than what the system yields back when they mix. Therefore, that deficit becomes manifest as the solution getting cold. Right? You feel it getting cold. The temperature would go down if you had a thermometer. Okay? So this is the enthalpy considerations of solution formation. Now, you also need to consider entropy, because as I've mentioned, entropy is in fact an enormous driving force for things to happen or not happen. So when you're considering entropy, you need to consider what happens to the solute and what happens to the solvent independently. And here's the thing. They go in opposite directions. Because if you consider what's happening with, let's say, a little sample of sodium chloride. Initially, the solid is highly organized. The ions are tightly packed in the crystal structure of the compound. As the solvent starts picking apart the solid and the particles in the solid start dispersing, what happened to the degree of order of the solid-solute particles? They were tightly ordered. Suddenly, they're all over the place, right? So that comes with an increase in the entropy of the solute. However, what happens to the solvent? Well, when particles dissolve and they have favorable and strong interactions with the solvent, what that ultimately results in is that the solvent particles, molecules, water in this case, they become highly organized and surround the dissolved particles. So the entropy of the solvent actually goes down. It gets ordered around the solvent particles, the solute particles, the ions in this particular example. It doesn't have to be ions. It can be glucose, whatever it is, right? So there's an ordering process of the ions, and it's very particular. The negative pieces of the water, which is oxygen, delta minus, are going to be sort of touching or surrounding the cationic components of the salt. So the sodiums are going to be sort of in contact with the oxygen piece of the water, very organized. The chloride is the opposite. The hydrogens, which are sort of sticking down here at an angle of 104.5, they're sort of interacting with the chloride ion. The negative pieces of the ion are touching or interacting with the positive parts of the water. The delta plus is on the hydrogens. So highly organized. So the delta S of the solvent becomes negative. So then the sum of those two, however much the solute becomes disordered, but however more the solvent becomes ordered, that leads to the net delta S of the solution process. So not only is there the energy that's released when the two come together, which is in combination with how much was absorbed by separating them, you also have to take into account how the relative entropies of the solute and solvent change. So this produces, these two possibilities produce the delta H of the solution process, whether it's exo or endothermic. And then the relative magnitudes of solute dispersion versus solvent organization leads to the net delta S. Ultimately, if you remember, again, delta G equals delta H minus T times delta S. Notice there's a temperature dependence as well, as we know, right? As long as that delta G is less than 0, the salt will continue to dissolve. It stops dissolving the moment delta G reaches 0. So at that point, the backwards and the forward processes are equally probable. No more solution at that point. So this is why T temperature will change solubility, because higher or lower will alter the factor that's in front of this parameter, and all that is needed is that this whole thing is negative. So different solutes will have different solubilities at different temperatures, because it all depends on the combination of these two things. As long as delta G is negative, the solution process will continue. So a couple of things that you also need to be mindful of. We had talked about this last semester when we introduced the concept of solutions. Now that we understand the molecular level, what's happening, depending on the attractive forces that exist between solute and solvent after they've mingled or mixed with each other, that can have an effect on the volume of the solution. If they attract each other very strongly, they're going to be more compact. If it's not that much, then they may be at a further distance from one another. And because the magnitude of the forces in the solution are not necessarily of identical magnitude in each of the two substances separate, this is what may lead to, in this case, it's a volume deficit. In other cases, it's a volume surplus. You can mix very precisely measured identical volumes of two liquids. I think this was ethanol and water or whatever it was. But notice, perfectly 50.00, this is to this, I think this is to the second decimal place, these volumetrics. Perfectly measure as precisely as you possibly can, 50 ml. Mixing them together, it does not add up to 100 ml. So this is why we keep saying you cannot assume that volumes are additive. If you don't require high levels of precision, okay, it's ish, 100-ish. But if you need very high precision, you cannot make that assumption. Okay, it's entirely due to these interactions that between solute, solvent, and then solute with solvent, they may not be perfectly aligned. So this little table is simply trying to summarize, give you some insight as to when would you expect a solution to form. And again, it's all based on the notion that delta G needs to be negative. If it's positive, it's not happening. So when you have an ionic or polar solute in a polar solvent, the delta H, depending on, again, whether it's endo or exo, it will be positive or negative. But if they're both polar, it's not going to be too big, the difference. It's going to be nearly thermoneutral. Typically for these types of substances, the delta S of the solute dispersing is much greater than the delta S of the solvent organizing itself. So typically the delta S is positive. If delta S is positive, and this is small positive or negative or nearly zero, again, delta H equals delta S minus T delta G, equals delta H minus T delta S. If this is a positive number, this is always positive. If this is small or zero, your delta G will be negative, and that substance will form a solution. If you're dealing with polar with nonpolar, there is absolutely zero attraction between solvent and solute. None. So therefore, the delta H of the solution will always be positive. Why? Separating the solute, separating the solvent, when they come together, they do not attract each other. There's going to be an enormous deficit. Okay? So that's always going to be positive. And then for reasons we're going to describe in a moment as to why oil and water do not mix, the delta S of the solution is very, very negative when you have things of opposite polarity. We'll explain why that is in a moment. So ultimately what happens is that the delta G is positive, there's no solution. And then you can analyze the exact converse of that, nonpolar with nonpolar for exactly the same reasons the solution will form, and polar with nonpolar was pretty much the same as up here. No solution will form. Okay? All right. So as a solution forms, heat can be released or absorbed. Solute particles can get ordered or disordered. Solvent particles can get ordered or disordered. And then delta G progressively becomes more and more negative as the solution forms, which is true. Okay? And the answer is? I hear D. The answer is A. The answer is A. Now, what did we say about delta G? The solution continues to form until delta G becomes 0. So what that truly means is that it starts negative because that allows solution to happen. When does it stop? When it reaches 0. So it's progressively getting less negative until it gets to the 0 point, and that's when it stops dissolving. All right? Solute particles always get disordered during solution formation. They will always separate. Solvent particles are always getting ordered during solution formation, because as the solution forms, they are ordering themselves around the solute. Okay? What can be a gamble is A. Heat can be absorbed, heat can be released. So it can get hot, it can get cold, or if it's perfectly thermoneutral, then there's no change in temperature. Okay? All right. What is wrong with these questions? Something's wrong with these questions on this chapter. I just don't get it. And it doesn't open when I hit the repo button. What time is it? Oh, we're good. All right.
I have a dumb question.
Yeah.
When an ion disassociates, is that technically considered a reaction, or
When what?
when the ion disassociates?
No, it's not a reaction. It's just a separation. Yep. Because their identity doesn't change. Yeah. In the case of the molecular compound that ionizes, that's a chemical reaction because it ceases to exist as a molecule, bonds have been broken, and it's now something else. Okay? But not dissociation. So everybody knows about this, right? Oil and water do not mix. So you can be very broad about it. Non-polar substances, organic materials, will not dissolve in water, right? So of course, we're talking about now focusing on oil. So why is that? Well, water is extremely polar, has no attraction for the oil molecules. So remember, in theory, to form a solution, the water molecules need to separate. The oil molecules need to separate. Both of those processes require energy absorption. If there was an attraction between them as they came together, energy would be released. But it's not. Nothing is released because there's zero attraction. So the entire process of separating them is delta H greater than 0, endothermic, nothing we get back in terms of them interacting with each other. Right? So they separate, and when they come back, in fact, this is even not happening. They're just up here. There's no attraction whatsoever, right? But the entropy is also critically important, and this is the key, right? So our enthalpy change is unfavorable. So what about entropy? Because it's all about delta G, remember, at the end, right? So entropy is, in fact, the biggest factor. So in order for individual oil molecules to dissolve, the water, because the water has zero attraction for the oil, the water molecules would have to be organized above and beyond normal, completely surrounding the individual oil particles and forming a cage around them so that the water molecules can interact not with the oil, for which they have no attraction to, but with themselves. They have to form like a cage and interact with the neighboring water molecule, with the other water molecule, with the other water molecule. So imagine if it were to dissolve, every single oil particle would have to form a cage, would have to be surrounded by a cage of water molecules, and they're interacting with themselves only. So what turns out to happen is that, well, if you get two particles of the oil together, they're going to interact with each other because they like each other. They have the same type of interactions over here, right? And therefore, that would then cause a larger cage of water molecules surrounding these two. It turns out that this larger cage, believe it or not, requires less water molecules than the multiple little ones. So what then ends up ultimately happening is that this is higher entropy. It's less ordered. Less ordered. That's what that means, right? Higher entropy is less ordered, right? So ultimately what happens is that the totality of the oil comes together with itself, and only at the interface between the oil and the water is where the water molecules are arranged to interact with themselves and not the oil, but by completely excluding the oil out of the water, that minimizes the unfavorable delta G, because ultimately what ends up happening is that delta G of solution is always positive. No solution will ever be able to form. Okay? All right. So, why is it that they don't mix? Dissolution is highly exothermic. Solvent entropy increases greatly. Net delta G is greater than 0. Or is it all of them? Okay? All right. And the answer is? What's the answer?
Don't look at me like that. I thought it was C.
The answer is C. The answer is C. The dissolution is highly endothermic, right? This is what we just said. What does that mean? No attraction. No attraction between water and oil molecules, all right? Therefore, heat separates them, endothermic, you don't get it back because they're not going to attract each other. 0, right? 0 attraction. So positive delta H. We just said that for the oil particles to mix and disperse, the water molecules would have to be extremely organized, right? The entropy goes down to ridiculously low values, right? So it decreases greatly for that solution to form. To minimize that decrease, and listen to what I'm saying, to minimize the decrease in entropy is why the water excludes the oil, and only at the interface between the two is where the water is organized. Otherwise, it would have to be organized throughout the entire the whole thing, right? So it's all about delta G, right? It's positive. It's not happening. Okay? So this process is exceedingly important in biochemistry. And what is known as the hydrophobic effect is this mutual exclusion of water and nonpolar substances when they encounter each other. They will not mix. The aqueous components will be in one place. The non-aqueous, non-hydrophilic, non-polar, let's use simpler terms. The non-polar components are not going to want to be in any way or shape or form wanting to be in contact with the water. They want to be in contact with themselves. So they exclude each other from each other, right? This is known as the hydrophobic effect. So it turns out that this effect is critically important in the three-dimensional structure and the chemical behavior and physical as well of all biological macromolecules. We're going to start talking about biochemistry at some point in the near future, because what this does as I've already alluded to with the oil and water, it minimizes the surface area of contact between these two phases that want nothing to do with each other. There's an entropic gain, again, less ordering of the water molecules. It only happens at the interface as opposed to around individual particles. There's also an enthalpic gain, heat energy. The water molecules reestablish the interactions with themselves to a greater extent than they would otherwise be, and thereby that is more favorable in terms of heat changes and exchanges. The same thing can be said for the oil-oil interactions. The oil particles are much better suited to interact with each other than with the water, so they also come together. So ultimately, this hydrophobic effect, in which they exclude each other, is energetically overall more favorable, and that's why they do not mix. So here's some cartoons trying to illustrate this process. Again, now imagine individual particles of nonpolar substances. Rather than the water having to organize itself around these pieces over here, turns out this little blue thing is actually polar. This is an amphiphilic substance. This is like a soap or detergent. But just focus your attention on this little piece over here. The water is highly organized, trying to interact with itself as opposed to interacting with this piece that has no attraction to. So rather than doing this with individual particles, this is what we've been saying, it's better to just have these three pieces come together and then the water simply organize itself around the bigger piece, right? But what ultimately ends up happening in the particular case of these substances that have what we call a polar head, and these pieces are non-polar tails, is that all of those come together and all of these tails end up accommodating themselves towards the center of this structure. It's a sphere that we call a micelle, and this is completely excluded from the water. The water stays outside, interacting with the polar blue heads, and there's a complete compartmentalization of the non-polar components from the polar components. So we'll talk about this in much more detail. Let me just get to this point. I have 1 minute, and this is related, and we'll finish with this. Here's another example of a drug interacting with a target. So let's say you have a non-polar drug, and the target of that drug is non-polar as well. Well, the water molecules will greatly arrange themselves, highly organized here and here. When these two come together, that allows for that interaction, and the water molecules are less organized. This is critically important in pharmacology. We'll talk about that more next time. The quiz, I think, covers up to the blood, so not this. Where we ended last time. There will be, yeah.